So we're going to keep working with our n choose k function. Now, right now we have a mathematical definition for n choose k, that binomial coefficient. So we have a way to mathematically calculate n choose k. And if you remember, if we have a set of n objects, how do we choose, how many different sets with k objects can we make from that, right? How many k size sets can we choose from those n possible objects? So that's the binomial coefficient. We have that definition. We're going to build a recursive definition for that now. So it's the same thing, it's just another way of arriving at it. And we're going to do that because recursion is very important in computer science. What is recursion? A recursive definition is defined by itself, which kind of makes no sense. But if you think about it like this. So do you remember when you were a kid, maybe you had one of those toy snakes where you had like a little tail and you could snap on a body segment, then a body segment, then a body segment. Let me do an awesome drawing of that for you. So you had the tail, and then you would snap on a body segment, and then another body segment, and then another body segment. So this was your base case, right? The smallest snake you could have is just a tail. And then this is defined by one body segment plus the tail. This is defined by one body segment plus whatever this is, right? This is defined by one body segment plus whatever this is, whatever comes after it. So we have a base case, a tail, and we have a general case, a body segment plus either the rest of the snake, which is either another body segment or a tail. That's how recursion works. That's what we're going to be doing to get the same formula that we did with the binomial coefficient. In order to make it a little bit clearer, I'm going to be talking about this, and I'm going to have on the right-hand side, I'm going to be giving our general definition. On the left-hand side, I'm going to give you a specific example, just to make these concepts a little bit more concrete, make it a little bit easier for you to follow. So for each of them, we have to define a base case, right? What is our base case? In the general sense, our base case is, what is the smallest n choose k that we can do? Well, from a set of 1, I can choose nothing. And if I choose nothing, then I have one possibility, which is the empty set, right? My other base case is from a set of 1, I can choose one item. Well, if I have to choose one thing and I only have one thing to choose from, then I only have one possibility, whatever it is from n that I'm choosing. Now let's look at, I'm only going to write it on one side here, but you get the idea. Let's look at the general case. So in the general case, suppose we have a set x, and x is made up of, x sub 1, x sub 2, all the way up to x sub n. So x sub n is our nth element. It doesn't have to be an order, it's not an ordered set, but just, it's the last element when we list it out. If we were to put that into concrete terms, we might have a set x of A, B, C, D, and E. And that E right there, that is our x sub n, right? That is our nth element. Okay, so that's a concrete example of our general set. Now again, what we want to find is how do we calculate C of n choose k? So we're counting how many subsets have k elements. Let's, just for the sake of example, let's make a subset S, and S has k elements. If you remember those lines, that means cardinality, the number of elements. So we're just going to make us S, and S is some subset of X, right? S is some subset of S with k elements. Going back to our concrete example, let's make k equal to 3. So we're going to make S some subset that has 3 elements in our concrete example. But we're not going to tell you what it is yet. Hold on a minute. Now we have a question to ask. Is x sub n part of our set S, which we haven't defined yet? And the answer is yes or no. So if the answer is yes, x sub n is a member, that means that S must be some set with k minus 1 elements plus x sub n, right? Because S has k elements. If it does have x sub n, then there's some set one smaller than k that does not have x sub n. So if we go back to our real world examples, those sets are AB, AC, AD, BC. So those are all the sets that are of size k minus 1, right? K, in this case, k is 3, so 2. They're of size 2, and they do not contain E. So if you add E to any one of those sets, one of them will be S in this situation where the answer to our question is yes, it does contain x sub n, right? So how many are there for that? Well, there are n minus 1 choose k minus 1 possibilities. N minus 1 because we're not counting x sub n, right? That's not part of the ones that we're choosing because we're looking at all the ones that don't contain it and assuming we will add it at the end. And then k minus 1 because all of these sets must be of the size 1 less than k. In our concrete example, that's going to be 2. And if you use our binomial coefficient formula to calculate to calculate 4 choose 2, you will come up with 1, 2, 3, 4, 5, 6. So it will work out. But remember, we're not using the formula, we're defining this recursively. The other possibility is that no, x sub n is not a member of S. So what are the possibilities? If we go back to our concrete example, what are the possibilities for a set S that is size k but doesn't contain x sub n? In this case, k is 3, so there are 3 elements, and it doesn't contain E. So those possible sets are, so there are 4 possible sets that do not contain x sub n, but are of size 3. Right? They do not contain, in this case, E, but are of size 3. In our more general example, we could define that as choose from n minus 1, since we know it doesn't contain x sub n, k elements. Right? So, in our general sense, we have now defined n choose k. We say n choose k is the same as n minus 1 choose k minus 1 plus n minus 1 choose k. Right? Because for each subset S with k elements, there are 2 possibilities. Either x of sub n is in it or it isn't. And we've already defined what how to figure out how many possibilities there are for when it is and how many possibilities there are for when it isn't. We add up the number of those possibilities, we get the total number of possibilities, which is n choose k. In our concrete example, that is 6 plus 4, which is 10. And if you go back to our binomial coefficient formula, you'll see that checks out. So we now have a recursive definition for n choose k. Because I can then figure out what is, n minus 1 choose k minus 1 by applying the same formula, right? My n shifts down, my k shifts down. And I can also, figure out the other side the same way until I get to my base case. And my base case, we know, is 1. So now I can start adding them up. So what I'm going to do now, let me go ahead and I'm going to give you a more formal recursive definition of n choose k using the full base case. I gave you some easy to understand examples, but let's use the full base case and let's kind of draw it out on a triangle, similar to the way they do in the book, right? Pascal's triangle. So my full base case, case 1, right? If from a set of 1 I choose 0, my only option is the empty set, so I have 1. From a set of 1 I choose 1 element, which again, I only have 1 possibility there. Case 3, from a set of 1 element, I choose some k besides 0 or 1. Well, that's got to be 0, right? Because if I only have 1 element, I can't choose anything but 0 or 1 from that set. And in any other case, if I have n choose k, we know that that is equal to n minus 1 choose k minus 1 plus n minus 1 choose k for any n greater than 1. Okay? These are the base cases that they define in the book, but there are actually a couple more that we could use. Really, let's say this is, we're going to call this A, just to be different. If we have n choose k, where k is greater than n, well, we know that's going to be 0, right? Because if we can't choose more from a set than the set contains, which is more general than number 3. B, let's say that if we have n choose 0, the answer is always going to be 1, right? Anytime we're choosing nothing, there's only one set we can get from that, the empty set. And we don't have to define this one, but we can. If we have n choose k and k is equal to n, well, that's going to be 1, right? I probably shouldn't put a equals there, but it is 1 if k is equal to n, which makes sense. If we're choosing every element from the set, there's only one way to do that. So those are a few tools that come in pretty handy as we do base cases. Let's go ahead and draw out our fun little chart. 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. Okay, so 0 choose 0 is obviously going to be 1, right? Because we said anything choose 0 is 1, according to B. 1 choose 0, according to case number 1, is going to be 1. 1 choose 1, according to case number 2, is going to be 1. Per rule B there, all of these are going to be 1 now, right? Because anytime we're choosing 0, the only set we can end up with is the empty set. So our first area that's kind of interesting is when we look at this, right? When we look at 2 choose 1. Because 2 choose 1 per rule number 4 is going to be 1 choose 0 plus 1 choose 1, right? And I hope you see how we got that. So based upon that, we're going to add these two together and we will get 2. And then 2 choose 2 per our rule C up there is going to be 1, which makes sense. And essentially all of this, that's all going to be 0. Because we cannot, remember, we can't choose more items than are in the set. That's always 0. So we can ignore that. Let's do one more. Let's do it truly recursively. Let's do this one right here. So we know that 3 choose 3 is going to be 1. What about 3 choose 2? So 3 choose 2. That's going to be 2 choose 1 plus 2 choose 2. Correct? So that's going to be these two right here. That's going to be 3. And by the same token, this is going to be 3 because that's going to be those two added together. 4 because that's going to be those two added together. 6 because that's going to be those two added together. 4 because it's those two, and then that's going to be 1, and on down. I'm not going to build the whole triangle for you. They do that in the book. But what they do a really bad job of in the book is tying this to a recursive definition. A recursive definition has a general case, right? Our general case is n choose k is the same as n minus 1 choose k minus 1 plus n minus 1 choose k, whatever those two are. Then you need to go figure out those two, and you drill down until you hit a base case. Once you have one of those base cases, you know it's going to be 1 or 0, and from there you can build up your definition. So I'm sure this wasn't clear. What I suggest is after watching this, go read example 7 and then come back and watch this again. This is a complicated one. This is one of the bigger ones. But this is important because we're going to do a lot of work on recursion this semester. Recursion is one of the most important concepts you can learn in computer science. They've designed whole languages around the whole concept of recursion. It's really vital. So take your time and understand it, or take your time trying to understand it. If you have any questions, ask in the forum below.